Let's start our day. So this morning we have Professor Domingos Viegas from Coimbra University in Portugal. Professor Viegas is very well known in the community, in particular because he has been organizing many international conferences. The International Conference on Fire
Research.
Fire research. Sorry, there is another F. Yeah,
Forest fire
research. Yeah. Thank you. That is the way I was introduced to the community on wine and fires and to the problem. And it's a very important conference in my view because it brings different communities together. It brings the fire engineers, the fire atmospheric scientists, and the fire ecologists, and beyond. And so this is a unique place where people can meet and exchange ideas. And one of our goals as a research committee is to emulate this model and multiply the opportunities for these different communities to exchange ideas together. With this, Domingos, the floor is yours. We're going to hear about extreme fire behavior.
Thank you very much, Arnaud. I thank you for putting all this summer course together. It's a privilege to be here with such a distinguished group of lecturers and of students as well. It is very good to say here. Okay, I'm going to talk about this topic of extreme fire behavior. I apologize, I know that in the audience there are people that probably saw earlier versions of this presentation, so it's for some of you will be a revision. Well, the contents is this. I'll give a brief introduction, speak about basics of fire behavior, just a quick revision, and go to extreme fire behavior, that is the main topic, and take some conclusions. As I said, I will review initially some basic aspects of fire behavior, orienting to what we designate extreme fire behavior. And this lecture is based in my activity since 1985 with my group. I must say that I was motivated to study this problem by a fire safety issue, an accident that occurred in 1985 in which 14 firefighters were killed. This accident occurred in this small canyon that you see in the foreground, and in it, as I said, 14 firefighters were killed. This was the only survivor, this man that is there. He lost his son and his brother in the accident. When this accident occurred, it was not very well explained to the public. People said that there was a change of wind. And when I visited the place a couple of years later, I understood that what happened there must have been very quick because the canyon was not very large and a group of firefighters could have got there if they had time. Then I decided to study these problems and in order to understand how fire spread, how it behaved, and how people also behaved in the face of fires to see if we could avoid this problem. I had a background on wind engineering, and I knew that wind was an important aspect, so I looked initially at this problem. And as I have an experimental background, I started also to study problems in the laboratory, because I think this is the good way to study these problems systematically. Later, I started to look at the whole of topography, and I learned to have great respect to topography, and especially to the issue of slopes and canyons. Of course, like so many, I worked with the Rotterdam model since 1972, but from the beginning, I started to challenge it and to see what we could do to improve some of its drawbacks. In this area, we cannot work alone. I have a team. These are 22 of my co-workers. 7 of us, we have a PhD, and there are different people from different nationalities, different backgrounds, and we are working full-time in the problem of forest fires. We work somehow in mathematical modeling. We do laboratory experiments, field experiments, and we also do observation of real fires. One of our assets is our fire lab that many of you know. Inside we have different test rigs that were designed by us. They are original and they help us to understand some of these problems that I mentioned. We have also a test field where every year we can make experiments, and we also go to real fires. This is where we are challenged by our lack of knowledge and the need to understand better some problems, and where we get inspiration to go promote our work. So we are going to speak about extreme fire behavior. It's important to distinguish between extreme wildfire events and extreme fire behavior. I'll not go deep in this because we will have the slides, but I'd like to refer to a work that was published some years ago by Teddy et al. I'm also a co-author, in which a multi-criteria is proposed to evaluate the extreme wildfire events. And it takes into account different aspects of fire. And as you'll see, when it comes to extreme wildfire events, the word wildfire behavior, sudden changes or unpredictable variations of fire intensity, erratic fire behavior are mentioned. The definition that is given in that article is here. So as you can see, different criteria are shown, and they don't need to be cumulative, but some of them must exist in a fire to it to be classified as an extreme wildfire event. This is, let's say, a more thorough description of the extreme wildfire event, and there is a great emphasis on fire behavior, on capacity of control, and also some on the effects. And as you can see there, for these extreme wildfire events, it is mentioned that the fire line intensity should be above a certain threshold. Of course, this is not along the whole perimeter of the fire. It can be only at a section and only for a certain time, but to be classified. But anyway, it has to be there. And it is mentioned these unpredictable variations. In this other table, different categories of fires are given. The first four are considered as normal fires, in the sense that they satisfy certain criteria, and the other ones above 10,000 kilowatt per meter are the extreme wildfire events. And as you can see, it's said there, they are chaotic and unpredictable fire spread. And this is the problem that we are facing, because these are the fires that create the major problems. In the previous work, I had proposed this definition of extreme fire behavior. And I must say that it is different. One thing is an extreme wildfire event, is a fire in which extreme fire behavior occurs. But this definition that I proposed, as you can see, it's quite loose. It doesn't have numbers, and it indicates that it is quite relative. Something that is extreme for a person in certain conditions may not be for that same person in other conditions. And I would like to stress the concept of knowledge, because the more we understand fire behavior, perhaps less surprised we are and less extreme we can consider some of the fires. In an extreme wildfire event, we'll certainly have what we call manifestations of extreme fire behavior, but it does not need to be a very large fire or even an extreme wildfire event to have some forms of extreme fire behavior. So they are not the same thing. That's why I would like to stress the differentiations between these. Okay, now let's look at some background on fire behavior properties. Of course, you know all of this, so I'll make use of that to go faster in this. I would like to, from the different fire behavior properties, I will retain my attention to the rate of spread. And I assume that you are interested on the head fire, its main direction of fire spread. So that's our relevance. We are not looking so much at the flanks, at the back of the fire, but this. The rate of spread is a vector. It has, in the surface, it has two components, but we can treat it as a scalar, because you can assume that we are following the head fire along a curvilinear line, and you can deal it with just a single component. It can be defined as an instantaneous value and as an average value. This is important to distinguish, let's say, in the context of what I am saying later, because quite often people refer to the rate of spread as an average value, something that happens between two times and it is constant in between. But I will go to the more, let's say, instantaneous value of the rate of spread. We know this concept of fire line intensity, and it is very important. we are aware that what contributes to change the fire line intensity is mostly the rate of spread. It can vary orders of magnitude, 4 orders of magnitude, and it's therefore important to know this rate of spread and to calculate it. So that's my main purpose. The other things are relatively constant. We know also that there are thresholds for the capacity of fighting, and there is even at the present state a value in which direct attack is not achievable. Okay, I'll also now refer to types and modes of fire behavior. These are 2 different concepts. I don't know if the words are appropriate, but these are the ones that I use. The types of fire behavior are those they depend on the stratus in which the fire is spreading: ground fires, surface fires, ground fires, and spot fires. My lecture will deal mostly with surface fires. Ground fires and spot fires, I said that they are directly extreme fire behavior. In the concept or in context of fire safety, I'm very much concerned with spot fires, but not so much with ground fires, because I've never heard of someone being killed because he was attempting to fight a ground fire. So this is our main purpose. As you know, surface fires can become ground fires and spot fires, but I'll not deal with that at the moment. Well, looking at surface fires, we can distinguish different modes. What I call marginal fire behavior, static fire behavior, and dynamic fire behavior. A marginal fire behavior is what was studied by Guilherme Rein and others, the ground fires and the extinction. I'll not deal much with this. The static fire behavior, it's the case in which the time is not taken into account. It's assumed that the properties are constant. So if the boundary conditions are constant, it's assumed that the rate of spread is constant. I must say that it occurs only in very restricted conditions. It is the exception. But most of the fire behavior modeling is based on this assumption of a static fire behavior. I prefer to study the dynamic fire behavior because it occurs in the large majority of the situations. Most cases, the fire behaves as a dynamic process, and that's why we should consider it. It's well known that the factors that affect fire spread, that modify its spread conditions, are described by this triangle of fire factors: the topography, meteorology, and vegetation, which is very often put like this. But as Albert said, I prefer to use the famous square of fire factors because I add the 4th dimension, that is time. It's chronological time. Because we notice that even when the other 3 parameters are constant, the fire may change its behavior, and that's why we express this thing. Going briefly along each factor, usually for topography, people retain terrain slope, but terrain curvature is also very important. It's sometimes overlooked, but it is important. It's not the same thing to deal with a plain slope or with a canyon. These are completely different situations. Vegetation, we know that it can be described by many parameters. I put great relevance on the moisture content because it changes the conditions, and we are dealing only with the surface layer. One important property that I introduce to the fuel bed is the residence time. That's the flaming combustion time in the fuel bed. It's more or less a characteristic of each fuel bed, but it may change according to the conditions. This is an important problem to understand the dynamic fire behavior. Meteorology, we know that is important. There are some factors that I consider conditioning because they modify the availability of fuels and their moisture content. And there are the determining parameters, which are the wind velocity and the vertical stability of the atmosphere. We will retain mainly the wind velocity as a parameter. So when we speak about wind, it's important to distinguish that a given local of the fire, the wind is the sum of the ambient wind and the fire-induced wind. And sometimes people forget this fire-induced wind. And this can be much superior to the ambient wind in many cases. So summarizing, we will retain these parameters of the three factors. And this leads us to the so-called static phi behavior. This is the domain of the Rothermel model. And it's where we can use the Rothermel model to estimate the rate of spread. If phi is going from point 1 to point 2, we can take the average rate of spread by this equation. One important property is what I call the basic rate of spread. That's the rate of spread of the phi line in the full bed without slope and without wind. We usually determine it in the laboratory. The Rothermel model can also provide this. The moisture content is a very important parameter for the rate of spread. This is the basic rate of spread of a full bed of pine needles, 1 kilogram per square meter. And as you can see, it's very important to predict correctly the moisture content, especially when it is low, because the rate of spread will vary dramatically. The Rothermel model then takes into account the effects of slope, wind, and also of the full beds using this function. You see R0 is the basic rate of spread, and this is the same formulation that Rothermel. That function depends on the wind, on slope. It's assumed that it's independent effects and its additive effect. And that also each one of that function depends on the full properties. In my work, I use very much this non-dimensional rate of spread because it's adequate for modeling. If you look at the effect of slope, we know that the positive slope will modify the rate of spread, and these are average values. I must say that the rate of spread is not constant, even in these experiments, but the average value, you can take it, and it shows how the rate of spread increases with positive slope, and the same thing with wind. The rate of spread increases with positive wind. And you'll notice that this non-dimensional value goes up to 30, 35 in these experiments. If we take the whole of wind and slope together, Rothermel assumed that it was an additive process. And although these experiments were not done for conditions rather than positive wind or positive slope, he extrapolated that there was an additive effect of these two factors. And he assumed that the prediction of a fire would be possible calculating the local rate of spread at each point. And at each point, the rate of spread depended on the local conditions of slope, wind, and the full bed properties. And this is quite not correct, because what happens at a given point in the fire perimeter depends on what happens in its surrounding. And its influence, it is not possible to do this. It was also assumed that the point fire would spread like an ellipse with two axes. And using this concept and Huygens principle, some fire growth models were built upon this concept. But if we study this problem carefully in the laboratory, and I think we were the first ones to do it in this table, we can see that for arbitrary conditions of wind and the slope direction, the spread of the fire is not an elliptical. It's not even a symmetrical perimeter, and it is always evolving. And as you can see in this diagram, there are different determinant values of the rate of spread. On this side, it is the positive wind and positive slope, and all that. So there is not a unique value of the rate of spread, and it is changing at all the perimeter and during all the time. So the concept of local fire spread is not very significant. And I looked some years ago at the problem of a line fire on a slope, and this fire was not initially horizontal. It had an angle with horizontal. I didn't know what to expect. According to the Huygens principle, this fire would travel parallel to itself. But doing these very simple experiments, we found that that was not the case. The fire would, let's say, go rotating. It, of course, had a translation, but it had a rotation, because there is a transfer of heat along the fire line, and the fire spread conditions are not the same. You see, here is a case in which the slope is fixed, the full bed is fixed, the wind is inexistent, but rate of spread varies from point of point, from one point to the other. So these are conditions that are changing in the course of time. That's where led us to study what I call the dynamic fire behavior. If you look at this picture, it was taken in a fire of shrubs of about 1 meter. You can immediately realize that in those flames there will be very important convective processes, and these processes will, of course, modify the ambient around the fire. In the laboratory, we can do careful experiments and we can analyze this. I proposed what I call the 3 canonic cases. And one of those cases is a point ignition in a slope, the other is a point ignition in a canyon, and the other one is a junction fire. If we look at repetitions of this experiment with 20 degrees, 30 degrees, and 40 degrees, you see that the rate of spread is changing in the course of time. That's a head fire. You'll see that it is oscillating, it's going up and down, but it is increasing. Sometimes it increases quite a lot and then comes suddenly down. But it is not constant. Of course, you can take an average value of this rate of spread, but the instantaneous value can be quite different from that average value. And depending on the size of your table, the average will be different. For the same slope, you'll have different values. And this is even more pronounced when you study canyons. And we started our study on canyons in this table. And if you see, if the intersection line of this canyon is 20 degrees on the top or 30 degrees in the bottom, the rate of spread is also oscillating and increasing. And in the bottom, it suddenly goes up very, very fast. This is what prompted us to introduce the term eruption. So this is the square of the factors. That's why we introduced this fourth size. Looking carefully at the behavior of the fires, not only at the laboratory, but in the field and also in the real fires, we came to the conclusion that the behavior of the fire is not, let's say, monotonic, it's oscillatory. Or I call it even intermittent. Intermittent in the sense that it tends to grow and then come down suddenly. And this is explained by the graph above, where you see the presence of a fire and the wind. And the wind is constant throughout the experiment, and the wind will modify the inclination of the flame, will give it more oxygen, so it will grow, will spread faster, and this process increases, and the rate of spread, as is shown in this graph here below, it increases. And but at the same time, there is an opposite flow on the other side, and this opposite flow grows, and the angle of the flame doesn't go below a certain value, and then the flame is stopped and becomes vertical again. And then another cycle is started. So this is what I call oscillatory or intermittent fire behavior. 1 month ago, we did a field experiment. Actually, we burned those 2 plots, and these were very ideal conditions because we were lucky there was strong wind, 8 meters per second, but it was perfectly aligned with the plots. We burned the initial one with a line ignition and the second one with a point ignition. And I could show you a video, but I think it would take too much time. This is the trace of the wind velocity. The burn took 5 minutes. It started at 12:03 and ended 5 minutes later. And the wind direction was also quite constant. But if you look at the rate of spread, it went up and down like this. So with the initial acceleration, deceleration, second acceleration, and like this. So it's not a constant. Although the full bed was homogeneous, as we could expect, as far as you can expect, the wind was constant and the direction was also constant, but the rate of spread is like this. And this is something that we find in different conditions. On the left is a laboratory experiment. On the center, another field experiment, and on the right side, a large fire that is reported in some cases. You can see the scales are completely different, both time and rate of spread values, and of course space scales are completely different, but the process is very similar. These are other cases, laboratory experiment again, and the bomb range fire. There it's not the rate of spread, it's fire line intensity, but we converted that to rate of spread, and the behavior is like that. So we found that the trace of the rate of spread in the course of time is like a cycle. If you look at the half cycle, the growing, it has that shape, and the decreasing has a different shape. Usually the time it takes to grow is larger than the time it takes to come down. This is something that is difficult to explain, or what was difficult to explain, in the sense that in the reports that you read about these fires, they have great difficulty in explaining why the fire reduced its rate of spread. So if you look at the amplitude of those oscillations and compare it with the average rate of spread, we find these oscillations in a wide range of situations. On the left are laboratory experiments, in the middle field experiments, and on the right are real fires. You can see we cover 4 orders of magnitude in the rate of spread. Yet the amplitude of the oscillations is proportional to the average rate of spread. But of course, this is a logarithmic scale. There is greater dispersion in the lower values, but you can see that the constant of proportionality is not the same for small fires and the large fires. For the very large fires, you'll see that this line has this constant 1.3, which has its consequences. If you look at this amplitude, we can correlate the ratio between the maximum and minimum value of the rate of spread in a cycle with this constant Kr. And if its value is large, the ratio between the maximum and the minimum value of the rate of spread in a cycle can be as high as 5. This is what, in my opinion, explains why with Rothermel model we cannot predict large fires. Because Rothermel model was derived from laboratory experiments, some field experiments. But what we are studying there is very different from what we have at the very large fires and at the very large scale. So we need to have a different approach to reach there. If you look at this report that Rothermel published in 1991 to study some very large ground fires, and he tried to use his surface fire behavior model, and he had to multiply his predictions by almost 4 to get the correct values, because he's not picking this convective process. And he wrote that the fire was 3.34 times faster than the predicted surface fire behavior. Yet people continue to use Rothermel model even to predict extreme fires and very large fires. And there is also this frequency of oscillations. And we studied them in all this range. And what is interesting is that this frequency has different clusters depending on the size of the fire. Above are the laboratory experiments, the field experiments in the middle, and the very large fires. Of course, the frequency decreases. This means that the larger the fire, the characteristic time, the period of the time oscillations increase as could be expected. And apparently, this frequency also increases linearly with the rate of spread, average rate of spread in this wide range of conditions, as you see. Okay. This is something that we are studying. It's not at all explored completely. But I take, let's say, a minute to comment on the concept that is very much used even in this course and in different instances of convective fire, of topographic fire, or wind-induced fire as types of fires. I think this is not correct, because wind and topography are quite always present, and convection is always there. And I show you this example. This is a sequence of 4 images that were taken in Israel, near Mount Carmel, in December 2010, after a fire in which 45 people were killed, and I was asked to study this fire. And these photos were actually taken by a helicopter from the police, and they gave me the photos. And if you look at the left side of the first image, so there is wind, more or less constant wind. It's flat terrain near the sea. And if you look at that, it is growing, and then it becomes a plume, and that plume dissipates. This is always happening in the fires. When the fire starts, if there is wind, constant wind, it will accelerate, it will create that plume, vertical plume, and then go down again. People say that it is wind-dominated fire or it's a plume-dominated fire, but it's both. These are different phases of fire spread. So they are, in my opinion, they are not purely, there may be purely, let's say, wind-dominated fire, what I call conflagrations. Case in which the wind is very strong, those are really, but in normal fires, you have all these aspects in sequence and repeating. So that's why I call attention and caution to the use of these terms. Okay. Now we come to the topic of extreme fire behavior. So I've been speaking about dynamic fire behavior, or the role of time and how it is described as oscillations. There are many manifestations of extreme fire behavior. I have listed these ones. There may be others. And I must say that possibly we introduced those two that are listed there in yellow, eruptive fires and junction fires. So what I mean is that perhaps some years ago I would not include those as manifestations of extreme fire behavior. And I say this because in some years we may find other manifestations of extreme fire behavior that we don't know yet. So this list is not complete. Conflagrations, I refer to them. There are situations in which the fires are spread with very strong wind, and there are historical examples of this. For example, in my country, in Portugal, on the 15th of October of 2017, in the same year in which you had the Pedro fire, we had a very tropical storm, and several fires were started, and they spread with south-north wind, as you can see there, and in a single day they burned 200,000 hectares. And this is one example of one such fire, and this is another one. These fires, we reconstructed the history, and as you can see, as I said before, if you are looking at the head fire, we can easily find the main part of the fire and analyze it, which we did. Let's look at two examples of the extreme fires. The first is the eruptive fires, and this is the fires in canyons. I call them eruptives because they are similar to eruptions. On the left you have a natural eruption, on the right it's a fire, 30-mil fire. When that picture was taken, there was an accident in which 4 people lost their lives in a ridge on the other side. As I said, we studied this problem in this test rig. It's a small test rig, 3 by 3 meters. The special case here is the concave shape of the terrain. So when you put fire ignition there, the shape of the terrain induces the wind that will feed that flame and will bring more oxygen, and the flame will increase. And when it increases, it will bring a call for more oxygen, and that is a feedback process. So the flame slowly is spreading faster and faster. Initially, there is a time in which it's almost quiet. It's what we call the incubation time. But then, if you look at it, it is growing, and at the end, it will be very different from the initial flame. This is what kills many people, because the firefighters go on the top. They see the small fire. They think they can go there and squeeze it with their boot, so they can wait for it with their car with water. Or if they are in the bottom, they think they can go and surround it quickly and surround it and kill the head of the fire. But if you don't do it quickly, they are caught by this. And this is a race that men cannot win. This is what Rotterdam studied about the Man Gulch accident. And as you see, the flames are completely different from the beginning. In this experiment that you saw, what is changing? not topography, not wind, not fuel. It's the same. It's time. It's in the course of time that the fire is doing this. And that's why we must pay attention to this problem. These are photos taken every 20 seconds apart, and this is the fuel bed that is burning there. When you burn it without slope, you have these flames, but as you could see, the flames were quite different. And if you look at this problem, you can study it, as I said, as a feedback process. With certain wind, the flame will increase, the rate of spread will increase, and this is in a given delta T, and in the next interval time, this will increase as well. And I propose this differential equation to describe the evolution of the rate of spread in the course of time. And if you see in that differential equation, there is a term that is the non-dimensional rate of spread divided minus 1. So if that term is different from 0, there will be an acceleration. And that term is equal to 0 only on flat ground and without wind. In all other conditions, there will be an acceleration. If we solve that solution, that differential equation, we can integrate it numerically. We will find this solution because the parameters can be determined for each fuel bed, and here is the comparison between the results and the model for pine needles. But if you have different fuels, of course, the properties will be different and the parameters will be different. I mentioned the residence time of the fuel bed. It has a certain value for pine needles. For straw, it is lower, and the processes happen faster. And if you go to the field, we did such an experiment some years ago. This canyon had around 200 meters long, and we had the same experience. We started to burn on the bottom. After 20 minutes, nothing was happening, but suddenly, in the last 10 minutes, it blew up and burned the entire canyon, as you can see here, after 22 minutes. So the time constants are different for different fuels. This is related to the residence time that I mentioned, and we studied that, and we can provide solutions of that equation for different fuels. On the left is for straw, or herbaceous, on the middle is for litter, and on the right is for shrubs. This curve for shrubs is very important in practical terms because it says that after 20-30 minutes the fire will erupt. And what happens is that the firefighters, they don't know in what condition they are. When they reach, they may be, let's say, see the fire dormant, but suddenly they are caught by that. And the initial conditions, the boundary conditions, depend on the shape of your canyon. If it is more closed, your starting point will be further up. So you'll have less time to reach the eruption. So these are important practical conditions. Here, we find very often in real cases. And I actually will present you a case study that I came across very early in my work in 2005. And this was an accident in which 2 people were killed. There was a slope, and the wind was blowing down slope, and the fire was started in the bottom of the slope, and it was spreading to the right. The firefighters were able to control it, except that it managed to enter the canyon. And when it entered the canyon, it blew up, and in 20 minutes burned the whole slope and killed those 2 people that were there. There was a weather station on the top, not as sophisticated like Craig showed us yesterday, but it was sufficient to give us data about what happened in that afternoon there. The temperature went up at the time of the accident to 56 degrees, 10-minute average. The wind direction turned 180 degrees, so it was downslope, it became upslope, and the wind velocity went average values to 60 kilometers per hour and with gusts of 92 kilometers per hour. You may say that it was some sudden meteorological event that happened that afternoon in that place. Some cold front that passed there. Not at all. But there are people that believe this. This was all caused by the fire. We checked all other possibilities, and this was caused by the fire. The second point that I'm going to describe, the second type of extreme fire, is what we call junction fires. This is when two fires merge. They create, of course, very important convective processes. And this problem that I'm going to describe came to my attention when some years ago I was invited by the New South Wales government to study the fire of Canberra and what had happened in that fire. As Alex Filkov mentioned on the first day, there were two fires, one that had started in New South Wales and the other that started in the Capital Territory. And in the given day with the very strong west wind, both of them went towards Canberra. And it was relevant to know which fire had caused what destruction. And I was asked to give my assessment. And the attorneys asked me what was the fire that occurred between them. They called the tongue fire because it has the shape of a tongue. I was embarrassed because I could not explain that. And I felt so embarrassed that when I came to Portugal, I decided to study this problem, to see what had happened. I visited the place several times, and I know that there was a tornado that destroyed trees there, and this tornado is even reported, and it had different bad consequences. Okay. In the laboratory, what we attempted different situations, but what brought us closer to the problem was these two linear fires ignited together. Let me see if I can show you. Okay, well, this is the sequence of images, and I'll try to show you also two videos if I manage to put them. On left, of course, it's an infrared video. On the right, if I manage to. Okay, it's a. Let's stop. Oh, not the other way. You see that the central point, the section point, is spreading very fast because of both convection and radiation, and it projects like a tongue fire. And this video takes around 30 seconds, so to burn 5 meters long, it's with 30 degrees slope. And the rates of spread of that point are the highest that we measure in the laboratory. And also, you can see here, in non-dimensional form, it goes up to 160 times the basic rate of spread, much higher than the slope or wind effect, and even the canyon. We did also field experiments with the same shape, with pyrotechnic ignition, to have simultaneous fires. And this is the images, infrared images of one of the plots. In 70 seconds, everything was burned. This plot would take us around 10 to 15 minutes to burn with a linear ignition up to the top, but with this situation, it's burned in 1 minute. And very strong convective effects are produced. You can see firewalls, one at each edge, and a tornado in the center. And this is what happened also in Canberra, of course, at the larger scale. And this is a problem that has no dimensions, has no scale. It's defined by an angle. So what happens at a given scale will happen at other scales. And here you can see laboratory experiments, field experiments, and Canberra case as well. The same happens with the canyon. I forgot to say that, because the canyon is a shape that is defined only by angles. It doesn't have a dimension there. I drew this yesterday at night to call the attention. If we have the fire line intensity, it's given by the product of those factors. And if we have given full load of 1 kilogram per square meter, in order to reach very high values of fire line intensity, we need to have values of this non-dimensional rate of spread of the order of 100 or more. And this can be achieved only in certain cases, not in all situations. And in these, the junction fires will reach it very easily. Let me show you a case study of these junction fires. In Portugal, we had, in 2017, very bad fires. These are the fires that burned that year. And in June 2017, we had fire of Pedrógão Grande. It started at 2 points below the electrical line in these two positions. And we could follow the fires with video cameras and, of course, with ground terrain. And what happened is at around 6 o'clock in the afternoon, there was a thunderstorm that was approaching from the south, and it interfered with the fires and dropped the fires to the ground. And so they were quite out of control before, and they became completely out of control after that. And they began to spread as two fires close to each other, and they began interfering, especially after 7:30. And as you can see in this sequence of images, for example, after 8 o'clock, the left fire is no longer going to the left to the sea, but it is converging with the one on the right side. And from this time on, the accidents occurred, and 66 people were killed. We reconstructed this fire very carefully in the field, and we did physical simulation of the fire in our laboratory, giving the initial conditions as the fire had. This is a superposition of the roads, and each dot is a place where lives were lost. In that circle is a stretch of a road, 200 meters, where 30 people were killed. And I'll try to show you this video. This is an infrared camera. This is the position of the fire at a certain time, around 7:30. And when the thunderstorm approached, we have wind, and the two fires spread together, and they begin to interfere. So hundreds of people that lived in that area, they are surrounded by the fire. And the survivors told me that wherever they went, they would go into the fire. And many people that would not go away from the fire in that day, they were very frightened because the fire was spreading in very, very bad form. People described things like this. There were flames separated from the ground, fireballs, as people said, crown trees that were burning from the top down. I don't claim that it was an independent crown fire, but rather fires burning from the top to down. And there were those tornadoes that I mentioned, trees broken, and we calculated that the wind necessary for this is at least 220 kilometers per hour. This is not atmospheric wind, but it is something that is induced by the fires and many other phenomena. And one of the worst things was in this stretch of the road. I was there in the next morning. I followed the pickup of everybody that on this road and elsewhere, and I studied each one of these accidents, tried to understand what people did, why they were caught by the fire. If we look at the rate of spread of the head fire, we find this process of acceleration and deceleration. In the canyon model, I had only studied the acceleration. People ask me, but will the fire go to infinite values? Of course, it could not go to infinite values. But then, as I showed, there will be induced flow on the opposite side that will retard the fire. And this will produce the deceleration. This is an ongoing work that we are doing, that we are fitting data points from acceleration phase of different case studies and deceleration phase. And we find that the mathematical model of acceleration and the deceleration fits. It fits also the deceleration phase. And as it starts from very high values, the deceleration is very strong, and this explains the non-symmetric form of the fire cycle. The growing is slow, but the decrease is very rapid because it starts with, and it's the same model, the same differential equation, only with negative term instead of a positive acceleration. It's a negative term. And this is something that we are studying now. We are also studying fire worlds, but I'll not say much thing about this. We studied also horizontal vortices. This was also mentioned by Alberto Simeoni on the first day, that when the fire reaches a ridge, it spreads laterally because of a vortex that is formed there, horizontal vortex. And this is found also in nature. It's interesting because when we study these things and when we speak with the people, firefighters, sometimes they give us the problems, but when we explain them, they immediately start to find this also in other cases. For example, these junction fires, I've come across different fires, more recent also in Portugal, in which similar processes can be identified. This is an interesting case that we studied of fire in a triangular-shaped hill with wind and in different conditions and the different fire spreads. And there are some fire behaviors that are, let's say, surprising in a certain sense, unexpected. But this was a very careful work that was done by one of my students, and he did also numerical simulation of the flow. And one thing we found is that the fire follows very well the flow pattern, the wind flow pattern. Of course, it modifies it. But if you have the, let's say, adiabatic flow calculation, it's a very good start to understand and to explain many features of the fire behavior. This is just an example. Those of you who visited our fire lab, saw that we were building this, what we call thermal combustion tunnel, in which we expect to build 3 layers of flow with different velocities and with different temperatures to create different stability conditions and to see how the fire behaves in them. So it is not yet ready, but I expect that it will be soon so that we can explore it. And I'm coming to practically to the end of my lecture, and I will show you this test, which is for me, let's say, somehow the corollary of my career, because after some years we were able to understand and eventually to explain what had happened in that canyon in which those firefighters were killed. In that accident, they were at the top of the canyon in one of the ridges, and they were called by the people of one village on the other side of the valley that was starting to get fires by lightning. And they decided to go down the canyon and go across the valley and to help those people. But when they entered the canyon, they lost the sight around them. And they did not realize that there was another fire approaching in the valley. And when they saw this fire, it was too late for them to escape. And let me show you what must have happened there. There is a wind of 1 meter per second. The video is accelerated in the interest of time, but this is not relevant because the acceleration is the same. Of course, in the reality, things happened much slower, let's say of the order of 20, 30 minutes, I would say. But you can see what happens when the fire approaches the canyon, although the canyon is at 90 degrees in direction of it does that. So those 15 firefighters that were there, they had almost no chance. Only one survived. That was at the bottom. He was lucky. He fell beside a wall of rock, and he was protected from the flames. But you see what happens. This is the behavior of canyons, and we have repeated this experiment with different wind conditions, with different angles of the canyon, even at the, let's say, obtuse angles in relation to the wind direction. It happens because the canyon has that capacity. We think of this fire, this accident that occurred in 1985, in which our fighters were very poorly equipped. They had no radios. They did not have vehicles to go there. They did not have aircraft to support them. But very similar thing happened here in the United States in 2013 in the Yarnell Mountain, with very well trained people, very well fit, with good equipment, with radios, with aircraft support. They were also fighting a fire on the top of a mountain. They had finished their job. They were going down to help people in the Yarnell city. They took a shortcut through a canyon, and when they entered the canyon, they lost the sight of an approaching fire that was coming below them. And when that fire reached their place, they deployed fire shelters but it was too late and 18 of them were killed there. You see the similarity between this canyon and what I showed you of Portugal. To conclude, I would say that the study of fire behavior is a central topic to understand all processes that are associated to wildfires. The behavior of a fire is dynamic due to the interaction between the hot gases and the environment. Our studies show that the fire behavior is oscillatory, so it's not a monotonic process, it goes up and down. And these oscillations have an intrinsic prediction error that is proportional to the average rate of spread. So the larger the fire, the larger rate of spread, in this case the extreme fires, so it is very difficult that we give the exact value of the, even if we try to calculate just the average rate of spread. Sometimes the fire may assume conditions of extreme fire behavior, which are the most challenging for those who have to manage and investigate wildfires, as it is our case. And extreme fire behavior is not synonymous of very large fires. Extreme fire behavior may occur even in relatively small fires, but it is more likely occurs in large fires. I studied an accident 2 or 3 years ago in Portugal of a 3-hectare fire in which one firefighter was killed. Of course, there was extreme fire behavior in that fire that surprised them and got them. Accidents in large fires involve usually extreme fire behavior processes, some of which are not yet well studied and well understood. With scientific research, we have to improve our knowledge on these processes and hopefully help nature to be like on the left side. This is a landscape in my country in which there was a fire in 2017. After the fire, you see this. People ask me if I believe that we'll go back to the previous condition. And I say that I believe yes. Okay. Thank you.
Very much, Domingos, for this impressive review, and also just as a comment to get started, it's very impressive to see the combination of laboratory scale experiments, field scale experiments, and forensic analysis of accidental fires. And it's the combination of all these 3 pieces that allow us to understand what's happening in these large fire events. We have time for questions. Yes, please.
Thank you very much for the presentation. Professor, I have a question on laboratory experimentation when one can observe eruptive fire behavior. So my question is, let's say that there's an experiment on the canyon equipment, and as I understand, the fire starts, and at some point it erupts. My question is, if you repeat the experiment with exactly the same condition, the eruption will take place on the same position in time and space, or this is random?
Well, provided that you can reconstruct the full bed in exactly the same conditions, there is no perturbation. Let's say in principle, at least in average, it should be the same point. Okay. So it is a time-dependent process, and as I explained, this acceleration will, let's say, occur, and maybe 5 centimeters ahead or 5 centimeters below, but it will occur sempre. I must tell you that we use our laboratory to train firefighters. Beside our laboratory, there is the firefighter school, where all firefighters from Portugal come to receive training on fire behavior, on forest fires. And we have a protocol. We teach them a lecture on extreme fire behavior, on accidents, and they come and spend 2 hours in the laboratory where they are exposed to these experiments, and we show them. And we show them the canyon fire. We repeat it in 2 different configurations, and it gets to their mind what happens. And I can tell you that more than 3,000, perhaps 5,000 Portuguese firefighters have come across our lab, and they spread the message to the others. Unfortunately, in the last 10 years, we did not have a canyon fire accident. Let's hope.
Tunnel that you just showed. How do you maintain both the wind velocity and temperature profile of, let's say, unstable boundary layer? I'm just curious about that.
In that thermal tunnel?
Yeah.
Okay, it can be controlled independently. I don't know if you saw the boxes that we have, big boxes. They are actually fed by climatic engines that can be either warmed or cooled, and each one of them has fans that can blow up to 8 meters per second at the exit, and the temperature can be varied between 5 degrees and 40 degrees. So we can independently change the temperature and velocity of each layer. So we can have a warm layer below and a cool above, and stable, or the contrary, warm on the top and cool in the bottom.
So it's going to be like basically just the profile till the inversion.
The atmosphere.
Not beyond the inversion.
That's right. Thank you.
Professor, thank you for the talk. And I have one question. So in your slides, you showed your non-dimensionalized rate of spread, right? And you have derived that equation. So in fire literature, if you see, whenever they report the rate of spread, so they report like rate of spread versus the wind velocity. So non-dimensionalization is not very much followed. So why is that? It is because of the time factor, which changes that. Or what is your thought on that?
No, I think we engineers, we work very much with non-dimensional parameters. We tend to find factors to make reference factors to make non-dimensional. And for me, for rate of spread, it's very obvious what I call the basic rate of spread, because this is the property of the full bed. It doesn't depend on anything else other than the full bed, the basic rate of spread. So if you make it non-dimensional with that value, you see, Rotterdam model is also using that. People don't realize, but it is using that. And it's very important for us in the experiments, because when we make a repetition of an experiment, we don't have the same conditions. For example, the moisture content may change from one day to the other, from one experiment to the other. And so if we use this non-dimensional form, if the conditions do not change very much, if they are linear variation, the function that defines the wind factor or slow factor will be the same, will not change very much, using this non-dimensional form. So I don't think it is correct to compare rate of spreads done in different laboratories with different full beds. But if you use the non-dimensional, it should be comparable. Okay.
We've done a lot of work using these lab-scale experiments to try and represent these events that are happening.
Large scale. Yes.
Have you found any challenges with scaling some of these results, or is just non-dimensionalizing things, does that help, or what sort of challenges do you face?
Okay. The question is if we have challenges transposing the results from the small scale to the large scale. Of course. And we are aware that we are not reproducing all the scales, all the non-dimensional parameters. But I think in this field we have to have good sense and to try to look at what is relevant and what is not so important. And if you are looking at the problem that depends on certain factor, and that is a dominant, the other become less relevant, and you can dismiss them. For example, in the canyon spread, of course there are maybe many other factors like the full bed or whatever, but the convective process is so overwhelming that it dominates all the process, and you can forget all the rest. It's defined, as I said, by geometry, and the geometry which is defined by angles, so there is no dimension scale there. So what you find in the laboratory can be observed in the field experiments and even large scale. I did not explain, but that case study that I described, in which that couple was killed, before that I had submitted a paper with that model of the canyon spread. And the paper was rejected because the review said that it was a small scale experiment, that it had nothing to do with the real case. In the meantime, I had this accident that occurred, I went there and I got this data, and in the reply to the reviewers, I included this case and showed this, and the paper was immediately accepted. So you see, sometimes it's necessary that people are killed for others to believe what we are doing. In the case of junction fire, it's a similar problem. It's defined by the angle, and the acceleration can be found at all scales, all dimensions of the problem. Of course, you can tell me, but where is the fruit number? Where is the this and that non-dimensional parameter? Okay, they are there, and we are not replicating that, we know, but we are studying some process that have, let's say, order of first order, and the others are perhaps second order. That's why we dismissed them.
Thank you very much for the talk. You described the phenomenological model based on the rate of spread. And 2 days ago, by Dr. McAllister, we saw some explanation based on fluid mechanics and instabilities. What is the link between the two?
Okay. We this morning I was talking with Mark, and I think that our work is complementary. We are studying fundamental aspects of high behavior, perhaps at different scales. If I'm not interpreting wrongly, but Mark will give a lecture later. He has been looking at the very detailed properties of the flames and fire spread, and looking at the very fine structures of the flames and oscillations. And I think this is part of the spectrum. I believe that I'm studying the continuation of this spectrum. I'm looking at the spread of the fire, which has also these oscillations that must be also and are related to those instabilities and all these things that you mentioned, that Sarah mentioned, that exist there. I myself, I did not close the loop, but I believe that there is something there. What I feel is that I'm showing and I'm exploring this field. I'm showing that there are some common things that happen in the whole spectrum of high behavior that perhaps have not been explored before and have to be explored. Mark and his group are doing excellent work, calling our attention to the fundamentals, to the need that we have to go to the basics. Because some people think that with Rothermel model everything is discovered. We don't need anything else. But we have to go much beyond that. And my contribution is just to draw the attention. The fire is not a static problem. There is a phrase that we say to the firefighter, what the fire is doing now may be very different from what he's doing 10 or 15 minutes later. And that can kill you. And this is our main lesson. This is what I'm doing. Further to that, we found that it's not only changing, but it is changing like ups and downs. What is the embedded there? We are studying that. We believe that it's convective process. I did not present here, but we are measuring the flow velocities in the flames in this oscillating process and trying to explain why in certain steps it accelerates and why it decelerates. And I think it's due to convection as well. Thank you.
Thank you. Great presentation. You showed that fire front oscillating, accelerating, decelerating, and it depends on scale. Just wonder, what's the rule of thumb? Let's say to measure rate of spread depends, what frequency of measuring rate of spread depends on the scale. Let's say for 1 meter fire, this is the frequency to define all this acceleration and large scale fire.
Let me correct one thing, Alex. You said that the acceleration depends on scale. Well, it happens in all scales.
The rate of change.
Yes. The amplitude or the period of change, it depends on the scales, on the dimensions of the flame. So regarding the rate of data acquisition, of course, if you have a time period, let's say of 10 seconds, you must have at least 3 or 4 to describe that period of change. So that's why it's very difficult sometimes to get data in the field because you have only very few data points on the rate of spread. Nowadays we have more information. We have more planes, more drones documenting fire, so it's easier to get this. But in the past, no, we have one here, another point there. In the laboratories, it's easier because we can measure everything more carefully as well.
Question over there.
The three-dimensional effect of the fire comes in play. Like, so if you do a point ignition and the fire is like continuously growing, and as it's growing, like obviously the point forces will increase. How does that come in play for the dynamic fire behavior? Because you mentioned that the depth is increasing and increasing, but like the parameter is also increasing overall.
That's right. That's a good question. I'm dealing with the problem as being one dimensional. I'm looking at the line of spread, but of course it's completely different if I'm looking at the point ignition fire or a line ignition fire. In reality, it will be always a three-dimensional problem, but it will be changing in different ways. For example, if you look at the point ignition fire in a slope like the experiment that I showed you, the head fire will tend to accelerate always, oscillating, but it will tend to accelerate always. The line ignition will spread fast initially, and then it form the V, and when this V is formed, the rate of spread goes down. Then it will go up again. So the three-dimensional comes from here. Of course, if the problem is more complex, we'll have other issues.
Questions? Actually, I have one question, if I may, Domingos. So we are trying, as you know, we are trying to simulate these effects at the level of a few tens of meters, but with a great spatial and temporal resolution. So we do see the three-dimensional variations along the flame line. So we are looking at a line fire and mimicking an infinite line fire. So it's a very academic-like configuration, but a good starting point. We are seeing the three-dimensional instabilities that Mark and Sarah have described, but we don't see, in terms of the rate of spread in time, we don't see the kind of time variation that you're suggesting. So, in your opinion, what are we missing? What pieces of the missing are we missing? These are fires that have fire line intensity on the order of a few megawatt per meter, so these are healthy fires, but we don't see the oscillation. These fires propagate at a well-established, steady rate of spread.
You don't see the oscillations then?
No.
Okay. Well, I don't know. I see them. I see them, and not only in my experiments, but also in the reports from many other people. And if you look at the reports, you can find this. I think that what happens may be the flow on the opposite side. Because according to my perception and what I describe is that the flame, when you have this wind, it will be inclined, and there will be a flow induced on the other direction. And this flow will accelerate because the space it has, if you have a conservation of mass here, if the space is less, and it will increase the velocity. And this velocity increase will tend to slow this fire and put it straight. This is what we observe in all fires. When you start a fire, it will initially grow and then more or less stop and go. This is what we observe. And then we'll have another cycle. Possibly, I don't know what's happening. And the flow on the opposite direction, perhaps it's not well caught. And this is coming back to the question that was put before. This happens both in two-dimensional or three-dimensional things. Although I'm considering only the symmetry plane as a unidimensional problem, but it happens in. I study this problem analytically as a two-dimensional problem, using even potential flow to describe the flow on the two sides of a plane that was inclined. And I was able to show, and we inclined the plane, the flame in this case, this velocity that is induced increases very much. And when this angle comes to 30 degrees, let's say this velocity becomes very large. So theoretically, I assume that the angle of the flames should not go below 30 degrees with the ground. So that concept of flame attachment that some people use in wildfires, I think it's not proper, because the fire will not touch the ground. They will be inclined but will not touch. The flames will spread on a reactive fuel bed, and they will burn the fuel. They will not be attached. They'll burn and advance faster, but the angle will not be below a certain value. And if you look at the literature, you do not find angles of the flames below a certain value, although people think that they can be zero.
Yes, okay. When we perform 3D simulation, because of the 3D behavior of the flame, it's very difficult to capture, to evaluate the rate of spread, because where we can evaluate an average somewhat, but it ensures this average does not reproduce the time evolution. But it ensures that when we can calculate the fire intensity from the consumption of fuel, of solid fuel, and it ensures that we observe this oscillation, because the structure of the fire, there is both peak and valley, vertically but also horizontally. Mm-hmm. And so with during the simulation, so it's quite dynamic, because vertically due to the puffing and stability due to buoyancy, and also horizontally. So I think it's a bridge between the two. Yes.
Maybe. Coming back to the work of Mark, it also Sarah showed the transverse up and down of the flame. Yeah. So we are not considering that. We are considering that the flame is something that is uniform, but we are considering the oscillations on the longitudinal direction, not the lateral direction. But of course, they must be related.
So how should we do the averaging? I didn't understand the difference between simulations and experiments. So how should we do it? So we take two endpoints and just take quasi-steady rate of spread, or should we focus on the flame at various time instants that have like a very small temporal resolution? What is your view on that?
Okay, my point is that we should pay attention to the variation of the rate of spread. It is not constant. Of course, the time that you take depends on the problem in which you are. For example, this quick acceleration of the fire and the very high rates of spread have great safety consequences. And we are in a safety course as well. So if you say that the average velocity is this, but the instantaneous value can be 3 or 4 times that, it is of great concern to the firefighters that are there. But it is also important to know that later the fire will go down. And then you'll have a lull, you have a period in which the fire will spread slowly. That's an opportunity, for example, to deploy guys or to take out people. And I've had reports of firefighters that were caught by the passage of these fire fronts, and in which they describe completely this process that I mentioned. They felt the wind coming from one direction, and then the fire, and then the wind from the other direction. They felt this.
When you are in the framework of a numerical simulation, which is easier than doing an experiment, then you have a leading edge of the heat release rate zone, you have a leading edge of the pyrolysis zone, so you can define the flame in different way, and that leading edge can be tracked, its position can be tracked in time, and then you take the derivative to get the rate of spread. In our simulations, when you do that, we don't see this type of fluctuation that Professor Viegas is mentioning. But again, we have to compare notes. We do see three-dimensional structure in space, so there will be, yes, variation of the structure of the flame spatially, but when you look, if you define the leading point as being the point that defines the leading edge position of the flame, then you don't see these fluctuations. So in an average sense, the rate of spread is steady for us. So we have a little bit of a difference there, and we need to reconcile our observations.
Yeah, I mean, this is a good conversation. It's a good question. So the question to me is whether or not in modeling fire spread, do we have to take into account the high frequency non-steadiness that we see and we can demonstrate and we can understand from the fluid mechanics standpoint? Do we have to literally represent that in order to have a physical model of fire spread, or what compromises can we make in order to achieve that end effect so that we achieve rate of spread values very much like what Professor Viegas is saying? So that's the question, right? We know what the physics is. Okay, what kind of approaches do we have to take? How literally do we have to take those processes to have a high fidelity physical model? We don't exactly know. There are different ways to deal with that, and we can have a good conversation about it. But you know, if you have to model the fluid mechanics of all of this, I think we're kind of from a standpoint of seeking a practical model of fire spread, because fluid mechanics is slow to calculate. So there have to be alternatives. We just have to find a way.
Yes. If I can imply from what Mark said, that possibly from this small-scale phenomenon that has been described and can be studied, we can learn things about fundamentals, but they may not be necessary to practical fire behavior model. But in my opinion, at least these large-scale oscillations that are observed and are reported in fires, they should be caught by the models. I don't know exactly how. My present explanation is that they can be explained by this process of acceleration, and the acceleration is very similar to the eruptive model, let's say to the feedback process. And what I postulate is that in the acceleration there is a contrary feedback process. Of course, there will not be the effect of oxygen attempting, but it will be a process of wind-induced that will retard the fire as a drag force. One important issue, and I'd like to come back to your problem, is if the flame is considered as a solid body. That's the question that I put you 2 days ago, because it's very important that somehow the flame is impermeable. There is no flow through the flame. The flow goes on one side and on the other. And this flow, when it increases, it will somehow retard the flame, and it will go decelerate. This is what we observe. I don't know if this is caught in the numerical models.
Well, in numerical models, we have the peak and trough structure that Sarah and Jason have studied, and so there is always places where the flow can go upstream of the flame, and so this three-dimensional structure plays a big role in our observation, and I think it's for that aspect of simulation is correct, because that we reproduce things that we observe in the field and in the lab. So we are happy about that. So I think the three-dimensional structure of the flame is very important to understand the dynamics of the flame. Yeah.
Sorry to interrupt.
No.
One comment about some of this stuff, and the presentation we're going to give right after this deals with a few of these questions also. But the model that we started developing years ago, actually when I started working on it, I wasn't starting out as working on a spread model. What I first wanted to look at is, I think what you're talking about a little, I was just interested in, so at the time we were really interested in sort of the puffing behavior of fires, and I was interested in how a fuel particle, a single fuel particle, reacts heating-wise to like alternating heating and cooling from, say, like a fluctuating flame puffing or something. And and I was wondering from the modeling side, does the average of the puffing of the heating give you the average heat up of the particle or not? And that depends on if it's a linear process, that heating, then you can make a shortcut often where the average of the inputs will give you the average output to this like heating, this convective heating of this particle sort of system. But if it's a very nonlinear process, the average of the inputs doesn't give you the average output, and that heating, the little experiment, kind of numerical experiments I was running showed some nonlinearity, not super strong, but I do. My intuition tells me that there are these heating time scales, right? And so on very, very large fires, like crown fires with 200-foot flames, the pulsation time and length scales are pretty large, the puffing. And if you think about the heating of a tiny particle, those puffing frequencies, one puff might be enough to ignite a bunch of particles. Whereas if it's small, fast puffing in a big particle, it might take a bunch of fluctuations to heat it to ignition. And so, in that case where you find particles in big long puffs of heat, that process may be the process that dominates the spread rate of the fire. Sort of the ultimate spread rate. So I think when we're talking about this and talking about modeling, we should keep these time and length scales in mind.
Yes, picking to what Jason says, if you look at the descriptions of fires or videos of fires, or observe fires like I do very often, you can see some fires that behave as a whole. They have their own life. They start spreading very fast and releasing lots of energy, and then they go, as you said, as a puff, and they go down. And that has very little to do with the other boundary conditions, the ambient conditions. It's the fire that has its own life, as is described very often in the reports. And so there must be some time period, some constant of time, that of course is dependent on the size of the problem, on the dimension of the problem. That's why we find these frequencies larger, lower and lower, let's say, when the fire has become very large.
And one comment I would like to make for the students is also, when you look at the flame, this flame has a structure, and the rate of spread is looking at one aspect of that structure, usually the most important one, because we want to know where the flame is, so the rate of spread makes sense. But this flame is going to be defined also by a certain depth, and an important aspect is to understand how long it's going to take to burn vegetation, so aspects of the residence time, for example, and that is going to control how much fuel is consumed by the passing flame. So there is, to me, the flame is a leading edge, and rate of spread characterize, how fast this leading edge is moving, and then a burnout edge, and usually that propagates at about the same speed, but not always. And then between the two lines, basically, you have a certain depth. And it does matter to know what this depth is also in your problem, okay? Because it's not the same flame if the flame is passing very fast for 5 to 10 seconds and the depth is 1 meter, or the flame now is 50 meter wide and is going to have a residence time of a minute. It is not the same effect locally of your fire. So we want to know where the fire is. That's a rate of spread problem. We want to know the impact on the fire and the total heat release rate, the total amount of fuel consumed. So you have to look at the full flame structure. So that's an important aspect too.
The fire intensity answer.
Yeah, so the fire intensity contains that information implicitly. It's going to be time for work, so let's thank Professor